All right, hello. Whoa. I'm Sagar Karandikar. I'm a PhD student in the architecture research group at Berkeley, advised by Krista. And I'm here to tell you about a project called FireSim, which does fast, cycle-accurate data center simulation using FPGAs in the public cloud. So before we jump into the actual simulation environment, we have a more important question to ask, and that is, why should we simulate data centers in the first place, right? The way people build data centers to this point is that they take commodity servers, commodity networks, stick them together, and that's your data center. Sure, there are logistical concerns like power delivery, cooling, and stuff like that, but really from an architect's perspective, there isn't anything too crazy going on. But given all of the kind of hardware scaling trends that we've taken for granted that are starting to end now, next generation data centers aren't going to be built only from commodity components. Right? And we're seeing a bunch of trends. One, the end of Moore's law is driving data center operators to integrate custom silicon in their cloud environments. So we see things like the Microsoft Brainwave FPGA model serving system, as well as Google's ASIC TPUs. In addition to this, we're seeing faster and faster networks, particularly shocking in contrast to the stagnation of individual server performance. And there's the promise of faster network technologies like silicon photonics on the horizon that can deliver terabits per second directly to a server die. On top of this, people are introducing new memory technologies like 3D XPoint that further deepen and complicate the memory hierarchy in the data center. And putting all of these things together, people are proposing a bunch of radically new data center organizations like disaggregated data centers, where you take all of the components that used to live on a single server blade in a data center, you break them up across this ultra high-speed network, and that gives you a bunch of advantages in things like resource allocation and scaling resources. And on top of this, custom hardware is changing faster than ever. As we all know, the open hardware movement, in addition to things like FPGAs in the cloud and new agile hardware design techniques, are really making it very easy to rapidly change the hardware under the feet of data center applications. So we see providers like AWS introducing FPGAs in their public cloud environments where developers can just go do whatever they want with the FPGAs, as well as companies like Microsoft integrating FPGAs more in the back end of their data center environments. So if we look at all these trends and we want to build a simulator that can prototype future data center systems, then we ask, what does our simulator actually need to be able to do? So obviously, it needs to be able to model hardware at scale. And in particular, if we care about these ultra low latency events in the data center, a lot of new applications care about latencies down to individual microseconds, then CPU microarchitecture matters, and we need to model it accurately. In addition to this, we need to model, obviously, the fast networks and switches and all of that infrastructure that's present in a data center. And now we need to model new novel accelerators, many of which you've seen in some previous talks. In addition to this, we need to be able to run real software. Nobody runs micro benchmarks at scale, so we need to be able to run a real operating system, a real networking stack. Generally, this means Linux, TCP/IP, and some of the new kernel bypass type things that you see in data center environments. On top of this, we want to run real application frameworks as well as real applications themselves. And lastly, we want to make this whole thing easy to use. So the way that we're going to get the last bit of performance out of these sorts of digital systems at scale is really to have collaboration between systems developers, system software developers, and architects. And this means that we need to run on a commodity platform that everyone can use. So if we take a step back and look at how people have evaluated computer systems in the past, there's sort of three main options. We can either build the real hardware, we can use a software simulator, or we can build some kind of hardware-accelerated simulator. So if we look at what it takes to build the hardware, as I'm sure all of you know, architects build hardware by writing RTL, something like Verilog or VHDL, or newer languages like Chisel. Then you validate, unit test, maybe formally verify some of the components in your system through RTL simulation. Then you go through the laborious process of pushing this through the ASIC tools, where you pay lots of money for licenses, sign NDAs for the backends, and then you iterate on this to get good QOR. And then finally, you send your design to the fab, give them lots of money, wait a long time, and you get some chips back. And so if you want to prototype a data center, you get those chips back, you network them together, and that's your data center prototype, right? Or in fact, you've just built the real data center. So if we're interested in doing research on new data center organizations, integrating all these new technologies into the data center, then this isn't really useful. We've kind of just built the real thing. It's very expensive, very slow, not a good research platform. Another option, like I said earlier, is to use a software simulator. There are lots of options out there. You've heard some of them so far today. And they make it really easy to prototype new hardware, right? Generally, you write something like C++ code that describes a piece of hardware, and you get a simulator, right? And it'll give you some numbers at the end. But it's also really easy to accidentally model something that you can't really build, right? These kinds of tools won't give you any feedback if you model a 2 gig L1 cache that takes 1 cycle to give you a result. That's obviously a bad thing to do, but if you are doing something, building some big complicated accelerator, it's very easy to accidentally make some weird assumptions that you don't notice in software simulation, and the tool won't complain, right? The tool will just simulate whatever you tell it. In addition to this, it's really slow to run these things. At best, you're going to get hundreds of kilo instructions per second for a single node simulation, which means you either have to run microbenchmarks or you have to use some other technique like sampling or skipping forward. So you're not really running the whole application. And then once you come up with a good design, if you want to build the real thing, you have to go write RTL anyway. So you did all this work, and then anyway, you have to go write RTL. You can take a bunch of these individual software simulators, though, network them together, and you can get some sort of distributed simulator. Another option is to build a hardware-accelerated simulator that tries to improve performance of simulation. Generally, with these sorts of tools, what you're doing is you're handwriting RTL models, right? The reason that we have to write RTL models is because if we just take some RTL and we plop it on an FPGA, it's not going to be timing accurate because our IOs are not timing accurate. So we need to write RTL models that kind of make our simulation timing accurate by controlling the stuff that actually runs on the FPGA. And then once you do that, whatever you've built is usually tied to some custom host platform. So if we look at a recent project called DIABLO, this was a rack of 24 FPGAs, custom built, that was put together to simulate 3,000 servers, 100 top-of-rack switches, and it all ran at 2.7 megahertz. So this is fast enough to boot Linux, run real applications like memcached. But the problems with this sort of setup are that you have to buy a really expensive host platform, and you're paying for this whole thing up front, right? If you want to scale further than this, you have to buy more FPGAs. If most of the experiments you run are smaller than this, you wasted a bunch of money. So that's one problem with this sort of approach. And then, like I alluded to in the first bullet point, you're writing abstract processor and RTL models here. So you can't take this RTL and just tape it out and build a real system if you wanted to. So you still need to do extra work to build the real thing after you use this kind of tool. So to sort of summarize all of these prior approaches, right, we can look at a bunch of potential metrics, like cost, an obvious one, right? Software simulator is going to be very cheap. You just run it on commodity machines. And then you can go all the way up to building the real hardware. It's the most expensive, but you get the real thing, right? And we see this trade-off in the runtime slowdown. Software simulator is going to be very slow. The real hardware is going to be as fast as the real hardware, right? There's another metric here, time to first cycle. What I mean by this is essentially you've written down your design. How long does it take to get something that can run instructions? Software simulator is going to be the fastest, right? You're generally just recompiling code. But if you build the real hardware, it's going to be the slowest, right? You have to go through all the CAD tools, send it off to a fab, get a chip back. If we look at whether or not we can sort of build the real thing out of one of these simulation environments in a software simulator, the answer is obviously no. Real hardware, answer is obviously yes. In a hardware-accelerated simulator, it could be no or yes, depending on what you look at. And the simulator I'll talk about in the rest of this talk, the answer is yes. Then the question is, can we run real software, right? Can we just take binaries that you would run on a real data center and run them in our simulator? In a software simulator, it's just too slow to do that. Real hardware can do that, right? It is the real data center. If we use a hardware-accelerated simulator, generally these things are fast enough. And I'll show you some results later on that really prove this. And then lastly, the question is whether we can run this simulation on a commodity platform. Right? Software simulator will run on a commodity platform. You just run it on any machine you have. The latter two, historically, you are not a commodity platform. Right? Either in the hardware case, you're building your specialized hardware, or in the hardware accelerated simulator case, you need to build some special simulation tool. So the question is, how can we do better, right? There's a reason people in the past did what they did. We have some new hardware trends that'll let us do better. So one, the reason we're all here, RISC-V gives us an open ISA, which lets us build software that runs on these open silicon-proven SoC implementations. And what we want to do is take these open RTL designs and prototype them directly in our data center simulator. And we want to be able to take advantage of these high productivity hardware design languages to let us do this automatically. So we want to automatically take RTL for a real SoC, transform it into a server blade simulation, network a bunch of them together, and do simulation like that. And then lastly, we had this problem of not being able to use a commodity platform to do fast simulation. Well, FPGAs in the cloud are going to solve that problem for us. So to summarize then, what are we building? We want a data center simulator that obviously models all the parts of a data center. We want to use a commodity host platform. In our case, we're going to use EC2 F1. We want to let users work either directly with RTL or directly with software models. We want to avoid that gray area of handwriting RTL models. And we're going to automate a bunch of stuff. And I'll talk about all of that stuff throughout the rest of this talk. And lastly, we want to be able to run real software, including the real operating system, running real applications on top. OK, so before we build our simulator then, let's look at the thing we're actually trying to simulate. What is our target design? So we're going to build sort of two components here. We're going to have server blades, and then our high-performance network that models the data center network. So our server blades are going to be built out of essentially quad-core RISC-V rocket cores that we model running at 3.2 gigahertz. Sort of standard L1, L2 cache setup, 16 gigs of DRAM. And then we add an Ethernet NIC to this design that here we say 200 gigabit per second because that's what I'm going to talk about throughout this talk. But it's really parameterizable. You can go as high as you want, as low as you want. It really just affects simulation speed. In addition to this, you can tack on optional accelerators, things like the Hwacha data parallel accelerator from Berkeley, as well as other accelerators you may have heard of. Then we're going to model a high-performance network. So this network is going to have a parameterizable bandwidth and link latency. So the examples I'll use throughout this talk have a 200 gigabit per second, 2 microsecond links. And we provide Ethernet by default as the link layer. But it's very easy to add your own link layer in the switch models and the NICs. We also automatically generate switch models with a configurable number of ports and a configurable topology across the data center. So the way you're going to build this simulation is you take the server blade RTL, you take these models for switches, you define in 10 lines or so a topology for your data center as a graph, essentially, built out of switches and server blades, as well as other types of blades you might want. And this will automatically construct and deploy the simulation on EC2 F1. So if we look at how we're going to map our simulation down to EC2 F1, we're going to break this up into two components again. So we're going to have our server simulation. We know that internally this has lots of fine-grained parallelism, right? This server designs have lots of gates that run in parallel, and we want to map those to a platform that's going to take advantage of that parallelism. So since we have the RTL, what we want to do is directly transform it into something that runs on the FPGA as a simulator. And I'll talk about that FAME1 transform on the next slide. But kind of the lesson here is that we're going to take the server simulation. We can do it fast on the FPGA. We're going to put it on the FPGA. Then the network simulation, there's sort of inherently less parallelism in something like a switch model, right? We can sort of get away with having a thread per port. And so we're going to put our switch models on the processors on the EC2 instances. And since they live on the processors, we're also going to use this to sort of coordinate simulation globally across many EC2 instances, as well as actually handle the network simulation itself. So real quick, we'll take a look at what it means to FAME1 transform RTL. So what we want to happen is, given some RTL in Chisel, we want to automatically transform it into a simulator. So what this means is we want to take this design, we want to wrap its top-level IOs, and essentially make it so that it'll only advance a cycle if it has a token that represents a value of input for that cycle on every single input. And if you want to see more about exactly what this FAME1 transform entails, I invite you to look at some earlier publications from CARV and ISCA 2016. So if we take these FAME1 transformed servers, what we can do is we can take that RTL, we can pack 4 of them on a single EC2 F1 FPGA. And so this means that we can pack 32 server simulations per F1 16x large. And an important thing to note here is that these are full rocket chips with L1, L2 cache, 16 gigs of DRAM each, and they can boot stuff like Linux on top. And so this equates to about 128 simulated cores on every F1 16x large too. And then running on the CPU here is a 32-port, 200 gigabit per second top-of-rack switch model. And we run 1 thread per port here because we have plenty of hardware threads to go around on these 16x large instances. So in aggregate, the simulation runs at 5 megahertz. So this is slightly better than a 1000x slowdown. In aggregate, this is running about 400 million instructions per second in the simulation. And this is much, much cheaper than previous simulation platforms like DIABLO, for example. So if you pay on demand, where you're guaranteed to not have your instances killed, you can run one of these nodes of simulation. So that's 32 server simulations for $13.20 an hour on Amazon, and $2.60 an hour if you're willing to take the risk of running in the spot market. So we built up the simulator sort of from scratch, right? We've built it up from RTL and custom-built switch models. So we want to show that we can reproduce real effects that people have observed at scale on real systems in our simulator. So there's some recent work from Eurosys 14 that shows thread imbalance on Memcached servers. So what I mean by thread imbalance is essentially if we take something like a 4-core server running Memcached, and we tell Memcached for some reason to use 1 extra thread. So we tell Memcached to use 5 threads. We're going to observe a big spike in our tail latency just from having that extra thread running, because Linux has to decide what to do with that thread, given that we have 1 more thread than the number of hardware threads in our system. So this was reported in a paper in Eurosys 14, and they have their own load generator that they wrote to run against Memcached. And so we take Memcached, we cross-compile it to run on RISC-V. We take their own load generator, cross-compile it to also run on RISC-V. And then we run it inside of our simulation. So we take 1 node and run it as a server, and we take a bunch of other nodes and have them run the load generator targeting that server. So then this graph that you see over here, this is from within our simulation. So this is measured from inside the simulation. We're varying the number of queries per second, and so this is the achieved number of queries per second in aggregate across all of those load generators. And then here we're observing what the request latency is across all of those clients. And so we see the effect that we're looking for here. So these bottom 2 lines that are overlapping, these represent the 50th percentile latency, the median latency for either 4 or 5 threads on the Memcached server that's running here, right? So we had quad-core rocket chips. And so we do either 4 or 5 threads to show thread imbalance. So in this bottom case, we expect nothing to change. And in fact, that's exactly what happens. We see no difference in the median request latency when we run in this case. However, if we look at the tail latency, if we look at the 95th percentile latency, this middle line here that sort of stops over here, that is our case where we tell the Memcached server to only use 4 threads. This top line, where the request latency blows up in the tail case, that's the case where we told our Memcached server to use 5 threads, so 1 extra thread. So just by doing this, we have the same load generation, the same version of Memcached, everything else is the same. We just told Memcached to use 1 extra thread. We see a 50% increase in tail latency. So we can reproduce results that have been shown on real systems inside of our simulator because we've sort of built it up from the ground truth RTL. So we can jump further and now scale to simulating thousands of nodes. So in this experiment, what we're trying to do is scale to simulating 1,000 nodes, 1,000 rocket chip-based quad-core nodes. This is, in aggregate, 4,096 cores. And then 32 top-of-rack switches deployed on 32 F1 16x large instances. And then to sort of complete the data center topology here, we have another root switch and then 4 aggregation switches that are sort of tying all of this together. So this diagram that you see on the right-hand side is the network topology and all of the nodes that we're simulating. In aggregate, this runs at 3.4 megahertz, so still a little bit better than a 1000x slowdown. In aggregate, this is running 13 billion instructions per second across the whole data center. And then we can do another experiment using memcached and the same mutilate load generator to sort of observe some latency effects if we change the request pattern across the data center. So in this case, what we're doing here in this experiment is we're taking half of these nodes, so 512 of them, and running memcached, taking the other 512 of them and running the load generator. We make one of these clients target exactly one other server, and we sort of vary how these requests cross the data center to get the different rows in this table. So the very first row that we see here, we're trying to establish a baseline. So we make sure that all of the requests stay within a single rack. So every request crosses only one top of rack switch, and then it gets a response from the server sort of within its own rack. And so we established some baseline numbers for 50th percentile latency, 95th percentile latency, and some aggregate queries per second. So you'll notice that the queries per second here are low. The reason is that we're trying to avoid server-side or client-side queuing delay. We're just trying to show the effect of adding hops in requests. And so we've kept the queries per second low here. But now, if we go to the next row in the table, what we're doing instead is we're forcing every request across at least an aggregation switch, right? And so what we would expect here is that we're going to add 4 hops, right? 2 hops on the request path and 2 hops on the response path. And so we expect that the 50th percentile latency is going to go up by about 4x. And that's exactly what happens, right? So the link latency in this case, like I mentioned earlier, is 2 microseconds. And so our 50th percentile latency goes up by about 8. On the other hand, you'll notice that the 95th percentile latency, if you just look across this whole column, kind of varies a lot, right? And this is sort of what we'd expect given the fact that we're not loading the system very much. And there are a lot of other factors that play into this 95th percentile tail latency besides just the number of hops. So we don't really see the extra hops reflected in the 95th percentile latency because it's sort of clouded by other factors. And then we can extend this to the cross data center case, and we see similar effects. And so this is simulating 1,000 RISC-V rocket-based server blades in the cloud, automatically derived from the RTL in simulation. OK, so to sum up, we can essentially prototype a data center based on any RISC-V core. So I mentioned Rocket Chip here. We can take anything written in Chisel and very easily transform it. We're also working on adding passes to be able to push Verilog designs through this flow. So you bring the SoCs, the accelerators, define some network topology, you push it through FireSim, and you get this automatically deployed high-performance distributed simulation. And then something else I haven't mentioned so far is that we can add a special SSH port or a special tap port on this top-level root switch. And you can now just SSH into the simulated system, and it looks like a real cluster. And these things are fast enough that you can SSH into them, type stuff, and it really feels like a real machine. It's just that when you go to measure timing inside, you get cycle-accurate results. You get realistic timing. OK, so thanks for staying this long and paying attention. We're really excited about this, and feel free to come talk to us about a lot of these things, including integrating out-of-order cores like Boom. Something else I wanted to point out is our functional network simulation. So if you're not interested in having timing-accurate network simulation, but you still want to be able to do cool things like SSH into your Rocket cores in the cloud, we can build a functional network simulation of a giant cluster of Rocket chips. And you can use this to do stuff like, as regression tests, automatically run all of SpecInt ref on Rocket chip at 150 megahertz in the cloud in less than 1 day because you can parallelize across a bunch of nodes. And if you want to try out this version, you can check out our demo and blog post on the AWS Compute blog. Yeah, and with that, I'd like to actually end. Thanks.